Good morning, everybody. How are you? We're all getting over yesterday, I guess. So today we're gonna start really diving into infectious disease dynamics, and we're going to talk mostly about immunizing infections. And I have a sense that you all have vast expertise in this already. So I'm going to try and thank you so much for the comments and suggestions you made yesterday. Like Ben and I have been including them and thinking about how to make this tend towards your interests. I also put the accent on Sao Paulo in the lecture slides now, so I want you to know. Okay. So this is where we were yesterday, immunizing infections, moving in a closed population. You get this sort of pattern. We worked through how the equations work. You put all of the world into 3 boxes. You're born susceptible. You can become infected with that feedback, and then you can recover. So simple, just to warm up here, what if the total population is at equilibrium? How would these equations change?
If there was no population change, yeah, you take out the mortality and birth maybe, and you say that it is actually only 2 equations, right? Because the total derivative of the population in time is 0, and that's it.
Great. So I think, so you suggested just taking away B and mu, right? Is there something else you could do?
Rather than that,
the derivative of the total population must be 0.
Mm-hmm. So this plus this must be 0, right?
Yes.
So then what happens? Do it in your heads, really quickly.
I'll need to make the calculations.
Come on. So this thing disappears. These 2 things disappear. Then we have Bn minus mu s minus mu I minus mu r equals 0. So B equals mu. Does that make sense?
Yes.
Everybody? Okay. So if we wanted, and that was exactly right. Tell me your name again. Sorry.
Adenilson.
Adenius.
Yes.
So as Adenius said, the way you would work this out is you do ds dt plus di dt plus dr dt equals 0. If you work through that, you come to B equals mu, which is this, okay? So I just changed that B to a mu. What's the requirement for infection to increase? This is so below you guys' level, but somebody tell me anyway.
The derivative of infections must be greater than 0?
Exactly. And we can work through what that looks like. So di dt is greater than 0. Transmission greater than gamma I plus mu I, right? We just move them over. And we end up with this expression, which if susceptibles is 1, gives us a definition of R0, right? Because you really, as soon as you find these conditions that vary around 1, you have your R0 definition. This is, I hope I introduced it yesterday. This is the number of new infections per infected individual in a completely susceptible population. It's a linchpin of much of what we do in thinking about infectious diseases. We can figure out what happens if S and I are at equilibrium. I will not insult you guys by asking you to work through it, but you can see that this is relatively straightforward. If di dt equals 0, so S star, the star indicates the equilibrium. You're obviously going to put these 2 on the other side and divide it by beta. Straightforward enough, okay? And the same for the I star. Somebody scream if this isn't making sense, otherwise I'm just going to keep going, okay? Okay. So we can add vaccination at birth. I made you guys do this yesterday. Very easy. You just take the way that births are feeding into the population, and you send them directly into this recovered class, because vaccination is assumed to be completely immunizing. And then what's left over, the 1 minus p, go into the susceptible class. Okay, now we get to the fun part. What is the proportion that we need to vaccinate to eliminate the infection? How would you get there? Let me remind myself. So what does it mean for the election? For the election? We're all sad about the election. But we must rally. For the infection to be eliminated, right? That means that I star is equal to what? Exactly. Yes? So we can work through what happens when I star is 0 to figure out what that vaccination proportion needs to be. This is okay? David's got it. David's doing it in his head. No, tell us. Oh, would you want to answer? That's fine too? No? Okay.
Is S over N 1 minus P. But mu have to be 0, I don't know, because yes, I think so. It's multiplying everything, right?
I have no idea. Let's find out. So we're saying I star should be equal to 0, yeah?
Yes.
This is where we're going. So mu n 1 minus, wow, that is bad handwriting. 1 minus p minus s star divided by beta s star equals 0. And I think what you're saying is that this needs to equal 0, right? Because the rest is. So
it's
n times 1 minus p minus equals s star. Why not? So s star divided by n, 1 minus p, so p equals 1 minus s over n. Is that right?
yes.
Not that I don't trust you. That is right, isn't it? Yeah. Yes. You're not tricking me. It's good. Okay, so we have this condition for R naught. And since S star is equal to, right, we wrote down on the previous slide mu plus gamma over beta, S star is actually the inverse of R naught, right? If you remember from the previous slide. And this actually, this is something I should have had a slide on, apologies. So if R naught is equal to beta divided by mu plus gamma, R naught is that condition for the di dt to be greater than 0. And you can see it because the transmission term is in the top here, and the sort of all the arrows that are going out of this box are in the bottom. So it's the rate of flow into the infected box divided by the rate of flow out. And so that gives you sort of quite naturally that R naught. Okay, so we can use this relationship for S star, and we're going to assume that n is 1, so we're looking at proportions of the population. So we have this critical fraction that we need to vaccinate. And this is immediately useful classic epidemiology, right? Because if we know what the R naught of an infection is, we have a sense of how hard it's going to be to eliminate it. So smallpox, the only disease on the planet that we have not just eliminated, but eradicated. So eliminated means within a constrained area, eradicated means the whole planet. Smallpox had an R naught of around 5. So what fraction of the population did we need to vaccinate for smallpox? Got it? Joao? Oh, no. So R naught is 5, so yes, 4. I thought you said 5/5, and I was like, no. 4/5, yes, exactly. Tell me your name again. Isabel, sorry, Isabel. Yes, exactly. Does that make sense to everybody? So 4/5, which is also 80%? 80%, yes. Okay. Measles has an R naught of around 20. You have to vaccinate just an incredible proportion of the population, so it's much harder. Okay, so another really important variable that we use in this world is R effective, which is R0 times S. So R0, number of new infections per infected individual in a completely susceptible population. R effective is what happens when the population isn't completely susceptible. So S is less than 1, okay? And so you can sort of imagine it on this graph here. As you move forward through time, we're multiplying, in this example, R0 is equal to 5, right? And this first infected individual in the completely susceptible population results in 5 new infections. But then we're multiplying 5 by the proportion susceptible, so it would fall and fall and fall and fall and fall. And does anyone want to guess what R effective would be at this point when the infected starts falling? Was that question clear? Yeah? Okay. Benny's giving me the nod. So the question is, what is R effective right here? It's the number of new infections per infected individual. Yes! Alice got it. Oh, did you say that? I'm not sure. Isabel, Joe, somebody said it. Okay. Or Cowie, whoever it was. Wonderful. Does that make sense to everybody? This thing is in decline. That means that R effective must be less than 1. Okay. And we can actually, so we know that the proportion, that critical proportion infected actually has to correspond to this world where the number of infected is cascading down. So R0 times S is less than 1. This gives us a different way of getting the same relationship, right? Because we're assuming that the proportion that you need to vaccinate is, the proportion that you vaccinate is 1 minus the proportion susceptible, right? So 1 minus PC equals S at that critical point, and therefore we end up with exactly the same relationship. Does that make sense? Good. Well, I'm not sure. Yes? Yes, okay. Good. Okay, so we've worked through these happy relationships, and there's just one more piece I want you to remember before we start moving forwards. And that is that we have this relationship ds/dt, didt, drdt. We've figured out what the equilibrium are. I've leaned on you to do that. And an important thing to observe is that the rate at which susceptibles become infected is this term here, right? Beta, it's actually beta I. That's kind of confusing. But the rate at which susceptibles become infected is beta I. And that means that the age of infection should be the inverse of this rate. Okay? It's pretty simple. And since we know what I star is, we can write down what beta I is at equilibrium. Beta I star equal to, beta times this term. You simplify out the betas, you do a little more mathemagic, and you end up with this relationship here because n over S star is equal to 1 over R0. Everyone happy with the mathemagic? Yes? It's not very magical mathemagic. Yes?
Could you explain the age of infection to be?
So the rate at which susceptibles become infected is this, right? You agreed beta times I. And so if that rate is very fast, the age of infection will be very low, right? Because you get infected very quickly. You move from this category to this category. If that rate is very slow, then it takes longer to get infected. And it's how that will work. But thank you for asking that question. I love questions. Okay, so then we can write our relationship for our average age of infection as this. Okay? More useful mathemagic. So can someone tell me what would happen to the average age of infection if the birth rate increases? And remember, you did some mathematic for me earlier where we established that the death rate and the birth rate were the same, so they're going to be mu here. This is not a trick question. Yes, exactly. The chorus. Decrease. So as the birth rate goes up, the average age of infection goes down. Could you tell me your name, the woman who asked the great question? Sorry? Amanda? Yes. Amanda. So as Amanda, the logic I just worked through for Amanda is also at play here, right? If the birth rate is really high, babies are pouring into the population very fast, and that means they're going to get infected earlier, right? It's the same basic process. So this may seem a little academic, a little strange, simple mathematic, but it has had weirdly enormous global consequences. And this is actually the first project I ever worked on in infectious diseases. So there is a virus called Rubella. It's like measles in many ways. It's directly transmitted. It's completely immunizing. It's very mild in children. So it's not like measles that kills children. This thing is very mild in children. And we wouldn't be talking about Rubella at all if it wasn't for the fact that mothers infected during pregnancy can give birth to a child with congenital Rubella syndrome. And this is very tragic. It's like deafness, blindness, mental problems, it's heart defects. It's a really, really tragic and completely preventable outcome because we have a cheap, effective, and safe vaccine, easily combined with the measles vaccine. So why wouldn't we just use it? It's a safe vaccine. Why wouldn't we use it? The issue is, as we've shown with these two relationships, vaccination can increase the average age of infection, right? Which follows on from what Amanda was asking about. If you vaccinate, you make the infection rare. It takes longer for a child to meet another child and get infected. So you have this weird paradox, right? If you could vaccinate everybody in the population, you'd be good. There's no problem. But if you can't, you could be pushing down the number of cases in children, where it's not really a problem, and increasing the number of cases in women of childbearing age, which is exactly where it's a problem. Okay? So it's a very subtle negative vaccine outcome. There's nothing wrong with the vaccine itself. It's the population-level consequences that can be problematic. Okay? And this just shows you what it looks like. Vaccination coverage goes up, the age of infection goes up, and you're pushing cases into that group of individuals who are having babies. So this is the fertility curve over age, an example of it. And the total cases could be lower, right? You definitely, if you're vaccinating, you're pushing down I-star, the total number of cases in the population is lower. But the problem is the number of cases in the one group of people you care about is higher. And in 1980, this chap called Knox, I should know his first name, I forget it, Gerald Knox, noticed this, noticed just the maths. That's all he noticed. And there was no data. And he pointed it out, and as a result, global health policy was made. And the Rubella vaccine was not introduced into most of Africa, India, all these places where it was felt that vaccination coverage could not reach the level that would be necessary to ensure that at a population scale things were better. So this is amazing, right? Like a theoretical result defined a global policy. Astonishing. The way I came into this was when I did my PhD on plants, on demography in plants, and then, like all the cool people, and then I really wanted to do something much more applied. And because I had a background in demography, they said, well, we have the problem for you. Because if you're a demographer, you're thinking about fertility, you're thinking about survival. So they put me on the Rubella question. And the thing I was asked to tackle was, this is obviously, these are conceptually, these make sense, but it doesn't tell you much about what we know to be what's happening in the world today, right? Like fertility rates are all over the place. The patterns of contact over age differ. Vaccination coverage, had both varied, but also had increased a lot. People wanted to revisit this because there were huge efforts underway to introduce the measles vaccine and to up the measles vaccine. And since you can combine the two, it seems like it would just be a stupid missed opportunity not to put Rubella in if it was safe to put Rubella in. So I was asked to attract this question, but using more nuance, using a vast array of sensitivity analysis and using more realistic models than these 2-compartment, 3-compartment models, right? So I built age-structured models. I drove them with what I knew about the demography in all the countries in question, and I made some predictions about what we thought would happen. And the results basically look like this. So this is vaccination coverage on the x-axis. This is the number of congenital Rubella syndrome cases we expect for 3 different levels of R0, because this is one of the complexities, right? We don't know precisely what R0 is, and R0 is dependent on what population you're in, probably, right? There was an estimate as high as 12 from Ethiopia. Estimates are generally somewhere in the range of 5 to 6. Okay? And so you can see this really captures the basic problem. As vaccination coverage increases. First, you get an increase in the number of CRS babies, because this is because you're pushing down the number of cases, but you're pushing up the number in women of childbearing age. But then after a particular stage, after this critical threshold, you'll fall back below what that threshold was before you started vaccinating. And so this was the number I was looking for. I was looking to find out what was the minimal coverage a country would have to have for us to be sure that you could make things better by introducing the vaccine. And this probably also makes sense to you. If the R0 is low, then the burden in the absence of vaccination is higher, right? Because a lower R0 means the disease is spreading more slowly from individual to individual, which means the average age is higher, which means that more women are being infected during their childbearing years. However, it's relatively easy. It takes a lower vaccination coverage to make things better if R0 is low. If R0 is high, then you're in a world where your burden in the absence of vaccination is actually quite low, because everyone's getting vaccinated super young, like age 5, age 6, age 7, and then they're protected for life. But what you have to do to make things better is actually really enormous. Like you have to vaccinate like 80, 90% of the population. And this is again because it's actually really hard to interrupt transmission of really fast transmitting infections. So we took these results and we showed them to WHO, and they said, this is very nice and it's completely useless. So does anyone have a sense of why they felt it was completely useless? Yeah? Precisely. That's exactly right. Tell me your name again? Joao. Okay. Exactly. So they said, this is nice, but like we're not sending people out to Sudan to estimate R0 to make a decision. Right? There's just no budget to do any of that kind of stuff at WHO. And so we ended up building a framework that encompassed uncertainty in R0. So that said, how confident were you, given everything we knew about the distribution of R0, that you would push down, that you would make things better. And from that expanded analysis, what we ended up showing was that, so there is a way in which the birth rate of the country also matters for reasons to do with, but WHO also told us that was too complicated, no one understood that kind of thing. So the WHO position paper that came out of this work stated that if you could achieve coverage of 80%, then you could go ahead and introduce the vaccine. Which is actually pretty conservative, right? Because 80% is also the threshold for elimination for R0 equals fine. But our vaccines, this is a difficult one for me to communicate, because although I know all the maths, it's got to be the public health official in every country that decides what the different trade-offs are here. Our vaccine programs, as we've really learnt over the last 2 years, are super fragile. And any perceived negative effects could be really awful. So there was so we now have 2 documented instances where the vaccine has led to an increase in congenital rubella syndrome, but not an increase like this, right? This is the long-term equilibrium outcome. There have been transient increases in congenital rubella syndrome due to transient dynamics in Costa Rica in the 90s and in Greece. And everything has sort of worked out fine, but it's not that these things don't happen, and so there's a lot of trade-offs to consider. Since this work, the vaccine has been introduced into many more countries in the world, partly as vast efforts to push measles vaccination up. But you can also see that any interruption of vaccination programs is a real problem here, because you allow individuals to remain susceptible for a long time. You might end up with vulnerable women of childbearing age. Okay, so that's the theory, the world-changing theory. But let's ask ourselves now, how realistic are these patterns? What are they missing? What are the really important bits of empirical data that this is abstracting over? And this is data on measles from London, so starting after, sort of around and after the Second World War, all the way up to 1965. Which is when vaccination really started. And you can see this doesn't look a lot like those smooth curves I showed, right? There's a lot more going on. And of the things that are going on, the 2 things that may spring out at you is there is this vast seasonality in outbreaks, and there's also a change in periodicity, right? So these dynamics are sort of annual, And then you move into the space where you're getting big outbreaks, but every 2 years instead of every year. So we need to expand our theoretical toolkit to think about these pieces, to pull in seasonality and periodicity. So the first thing that, so this is work by Brian Grenfell, who's a very beloved friend and mentor. And he noticed that over the same time course, you can see that births really peaked. So this is after the Second World War, the baby boom. The soldiers came back. There was a huge number of babies. And then people got tired of having babies, and women probably. And there was a decline, and then it's increased. But if you map that onto what's happening in the periodicity of so you get annual dynamics here and biannual dynamics there, it kind of, I think it sort of intuitively makes sense. If you were pouring babies into the system, you can have an outbreak every year, but if you slow that down, then you might end up having an outbreak every other year, because there's just not enough fuel on the fire. Not that babies are fuel, but you know what I mean. There's a piece missing though, right, to really make sense of this. And that is that there is clearly an important part of this dynamic is that there are seasonal fluctuations, right? There's got to be something driving this outbreak every year, the fact that there's an outbreak every year. And that's what's allowing this like annual to biannual type dynamic. It's like you're pushing a swing kind of really fast in this first bit, and then you slow down the pushing in the second part. But you need that pendulum of the swing. Okay. And so another really clever thing that Brian did as part of this work was he noticed that you could use, so you know we're missing a piece from our SIR model right here. So if you assume that S plus I plus R equals N, you only need S plus I. But what we have here is only I, right? And this is generally the case in any surveillance system. We only know who's infected. But to a first approximation, it's very reasonable to assume that before vaccination, everybody got measles. There's a quote from a book, Three Men in the Boat, which says, measles is like love, everybody gets it. And this was true pre-vaccination. And so what you can do is you can say, okay, I'm going to take the time series of births, which we have here, and the time series of cases. I'm going to assume that everybody who's ever born gets infected. I can figure out who's susceptible. And we can follow up on the details if you're interested. And then, having in hand who is susceptible and who is infected, I can write down an expression for infecteds in 1 generation time are going to be a function of infecteds today times susceptibles today times transmission that occurs. This makes sense to everybody? This is basically just a discrete time version of what we've been writing down to this point. And the reason it works is because the generation time of measles, so the average time separating infection in one individual from infection in the next, is 2 weeks. And it's a pretty crisp 2 weeks. There's not a lot of variance in how long that lasts. Okay. So the next thing Brian did was he figured out you could extract this just using simple regression tools. This is Brian actually in Otto Bjornstad. Anyone want to hazard a guess how? I think this might be a question. I mean, I'm sure some of you could actually write down lovely, intricate Poisson models to do this. But the way they did it is the simplest way in the world. It's put it on a log scale, right? And you put it on a log scale, your multiplications turn into additions, and you can write down a regression which says log IT plus 1 is log of this transmission plus this offset plus whatever error there is. And you would offset this because you don't think there's parameters on these pieces, right? You're just trying to get at what's going on. And you would fit, say, a different parameter for every bi-week of the year, every month of the year, whatever you thought was how much that seasonal swing was driving the pattern, okay? And how much data you had to inform it. Does this make sense to everybody? I'm not sure. Zhao, it makes sense to the Zhaos, so that's fine. Yes? And there's a bit of, if you wish to replicate it, there is the bit of code that goes through how you would do this. And if you do that, so now you can estimate a transmission term. So in every year for January, you find the transmission term across those, I think it's 20 years from 45 to 65. You estimate the transmission in January in 45, and 46, and 47, the transmission in February, 45, etc. And you get a pattern that looks like this. So it's high early in the year, and then it falls very specifically exactly when the Easter holiday happens. And then it falls again very specifically exactly when the summer holiday happens for schools. And then it comes up again. And so there's a very strong suggestion here that what's driving the infection, what's driving the seasonality, is the timing of school holidays, right? There's no reason there's no like climate variable. There's no like sudden rainfall that happens every year in the 9th week of the year, right? so this pattern hints at what the mechanism is. It's not distinctive proof, but it gives you a strong suggestion, and it's a suggestion that makes sense. This is a childhood infection. Most children are infected around age 5 or 6. This is the pattern we expect. And then if you take this seasonal transmission pattern, combine it with the births, you can simulate these dynamics unbelievably precisely. I mean, you can simulate 40 years of dynamics just using the 20-odd parameters from this and a starting proportion susceptible. And then you got it. It's amazing. It's really, really cool. So yes. We can also move back to our theory to think about broadly what we expect to happen. And but that can be done very simply by adding a seasonal fluctuation in our transmission parameter. Right? So this looks exactly like the DSDIDR that we had before. Wow, that's a mistake. Ignore that. These are Ds, guys. These are Ds. See them as Ds. Right, because delta is embarrassing. Anyway, probably Benny's fault. And there's a number of ways you can do that, but one way is to use this relationship here, where transmission at every time step over the year is driven by some cosine function, because these things fluctuate in a pleasing fashion. And if you do that, you can recover, instead of recovering this sort of equilibrium after, as Talis pointed out, some transient fluctuations, you get these seasonal cycles. And if you narrow in on the infecteds, they sort of look a bit like this. And then we can write down what the phase plane would be. This is, again, something, yes, David? This is correct, but why is it correct? So if we start off with susceptibles, say here, what's going to happen? So lots of susceptibles, infectives are going to go up. Exactly. Yes, we'll do the dance together. Exactly. Thank you. So that is exactly what the phase plane looks like. And you can sort of track it, basically across what those time cycles look like. The interesting thing is, our analysis of measles in England and Wales, or at least skimming the data, suggests that you will expect changes in periodicity as a function of the birth rate. And if you double the birth rate, this is exactly what you see in this simple model. Again, the code is here if you want to try it. You end up with super wacky, like double cycles in a year that collapse, double cycles and then collapse, etc. So you get super weird phase planes and really fun stuff, which I'd love to see Debbie dance. But so the sort of two inputs, that seasonal fluctuation in transmission and the pattern of it, and the other input, which is the birth rate, so how fast susceptibles are pouring into the population, will determine how cases shake out both within years and across years. And we had a lovely postdoc, also called Ben, who showed that actually under certain circumstances you can get chaotic dynamics. And pre-vaccination in the United States, measles looked chaotic, which is quite fun. I mean, not great for prediction. Fantastic. So many children died. No, let's just move on. Okay, so we've gone through an example of childhood, how fluctuations associated with children coming together in schools might drive transmission. Are there any other examples? Like, why else might you get seasonal fluctuations in transmission? Right? And the school example is like literally children are close to each other, there's an increased probability of transmission, they're far apart, it isn't. The fact that it's seasonal is because we human beings are seasonal. We behave in a seasonal manner. What else might be going on? Yes, oh, yeah, yeah.
Yeah, the weather.
The weather.
Winter, for example.
And so how specifically the weather?
Well, when it's winter, for example, people tend to stay more at home.
Ah,
Yes. And then airborne diseases can be more easily transmitted
how does that happen?
because they are in closer contact and in a close environment.
So you're, this is a wonderful answer. Tell me your name?
Julia.
Julia. So as Julia says, again, we could imagine that climate would shape human behavior that would lead to greater transmission. But I was thinking of even a simpler level. João?
The vector-borne disease.
Great. Expand.
The reproductive cycle depends on the weather. So like here in Brazil, when we are in the summer, we had a lot of mosquitoes. They are transmitting this type of diseases in this field.
That's exactly right. So another great biological driver that has nothing to do with our behavior. Do you have one? No, you're just waving. No? She's in. Come on. So we have human behavior, we have vectors. What about waterborne diseases like cholera? Flooding, seasonal flooding could shape the transmission of cholera. There's also, I don't know if you guys remember, oh, do you have one? No. During SARS-CoV-2, people got really exercised about whether there would be a climatic effect on transmission. And they were basing it on what we know about influenza. And although, as Julia said, human behavior might be part of that, we don't actually know for sure. But what we do know for sure is that virus particles fall out of the air in a different way when the humidity is higher versus lower. So the viral particles stay suspended for longer in cold, dry air. So you end up with, as João said, the weather, the climate drivers really matter, but they matter potentially at all scales. Yes? So suddenly a vast amount of biology becomes tediously necessary. Just a few examples here. So we think that the pathogen's survival in the air might be shaped by absolute humidity. It might be shaping how it falls out of the air. We know that for our own host defenses, quite apart from our behavior, how our mucus is functioning is actually, it's depleted by pollution in Sao Paulo, but also dry weather at certain times of year. And then aggregation, as Julia mentioned. For pathogens which have an environmental reservoir, we're in a world where cholera, for example, might be worse at particular times of year. There are tons of vector-borne pathogens, as João mentioned, and their fertility, their development happens faster at higher temperatures, but if it's too high, then they end up dying, so there's an interesting optimal they should be in, and it's a very interesting question what that means in a warming world, right? Is malaria going to expand or is it going to decrease, and how does that intersect with our control efforts? Another really funky piece of human exposure is that, when it's hot, people sleep under bed nets less because it's just uncomfortable. And that can increase vector-borne transmission. And finally, it's easy to forget them, but they also matter. There are tons of zoonotic diseases that actually intersect with our populations quite a lot, like hantavirus, which you find in deer mice, and deer mice have huge seasonal cycles. Okay, so lots and lots of things can happen. And there's many ways, a lot of what we do actually in our lab is try and do the detective work to figure out which piece of these is responsible. And it's a complete headache, right? Because everything is going up and down at the same time. Right? Temperature is changing up and down at the same time. So is the numbers of infections. That doesn't mean that temperature is driving number of infections. Right? If you had made that conclusion from measles, you would have been completely wrong, because it's actually about childhood infection. So there's a lot of really subtle work at trying to look for anomalies, so years that are more hot or more cold, etc., at particular times of year. And you can use the same sort of regression tools where you figure out what transmission is now at every time step, not just in every season, and then you pull together statistical models that control for everything you can think of. Carefully though, right? Not throwing in every variable in a mad way. There's a postdoc, there's faculty at Brown, Rachel Baker, who does a lot of really beautiful work on this. And one of the papers we've suggested, or one of the themes we've suggested, would be sort of going into how you do this detective work to probe what's going on. Okay. So we've talked about seasonal fluctuations, how they might drive outcomes. If there are any questions, please do scream or something. I'm now going to turn a little bit, because this became so absolutely manifestly important during the coronavirus pandemic, to the role of chance events, right? We've talked about these things which drive transmission which we can model deterministically, but of course chance matters too. And if we look at these immunizing infections again, what I'd showed you before was actually the number of cases in every week of the year across this time span for London. And if you go to these smaller cities, so Leicester, for example, or Runcorn, I don't know where that is either, but it's somewhere in England. People live there, probably. Then you see that the fluctuations are like more and more, are smaller and smaller, which isn't shocking, there's fewer people. But also they're spending a lot of their time extinct, right? So there's actually no measles in many weeks of the year in Runcorn. So there's no setting aside the probability of extinction of infectious diseases, right? Like everything else on this planet, they're at risk of disappearing, although we'd like it to happen faster for most of them. And so if you plot out the probability of extinction, which you can get from branching process approaches, as a function of R0, of course it's 1 if R0 is less than 1. We know these things are going to extinction. And then it declines as R0 increases, but it never goes to 0. And of course, this is making tons of assumptions about large, well-mixed populations, etc. But even at really, really high R0, you're never going to get a 0 probability of extinction, because there's always, the chance that you fall over dead before you transmit, something else happens. So we have to, in our considering how immunizing infections work in the real world, we have to consider the role of chance. We have to bring that into play. And so if we look again at these measles time series, we have to think about the fact that not only the seasonal fluctuations, not only does susceptibles pouring into the population matter, the role of chance actually matters. And there's this epidemiologist called Bartlett who first asked this question. And what he did was he took these time series and he plotted the proportion of time that extinction had happened. So the proportion of weeks during which measles reports were 0 in each of these different locations. So population size here on the log scale, this was for hundreds of cities across the UK, and then the proportion of zeros in the time series. So what pattern, what are we expecting here? What's the relationship you think we'll see? I like this gesture approach. So as Zhao said, right? Does that make sense to everybody? So if there's a very tiny population, you're flipping coins, but you're not flipping a lot of coins, right? So you're very likely to get extinction easily. If there's a vast population, you're less likely to have extinction occur. This is what the data looks like. And you have all this data if you wish to make these sorts of populations projections or plots. These are just some of the names. There's Runcorn, there's Leicester, and then way out here is London. And the concept that Bartlett came up with based on this work was the idea of something called critical community size. And he referred to this as the size above which stochastic extinction does not occur. There's just enough chains of transmission that you're just not going to lose this infection. Okay? And it's really important, I think, to note that this is an empirical measure. So it's not, if you simulated the dynamics of measles in cities of different population sizes, however realistic that model was, it would not capture this quantity unless it included introductions, right? So the rate at which you're getting weeks with no cases in Runcorn is a function of how rapidly things are going extinct in Runcorn, but also people are turning up and reseeding the infection. So there's two sides to that coin. This is an empirical measure that captures both the inherent dynamics of measles in a city, but also how much measles is being reintroduced into the city. And one of the nice pieces that you can pull out from this is that you can use this information to actually get a sense of what the landscape looks like for the pathogen, so for something like measles. If you imagine you're in a particular city, there's a measles outbreak that then goes extinct, and then you wait a little while, and then some little kid turns up with measles and coughs at your child, and suddenly there's a measles outbreak, and this happens. So that tells you, that you're not living on an island that no one comes to. People do turn up with measles. But there's another piece of information there, which is that the length of this period of time, if that period of time had been longer, that suggests that you're living in a more remote location, because it's taken longer for someone to turn up and give your child measles. And you can actually use this information, so these waiting times to reintroduction, to estimate how connected every city is to the overall population from the perspective of the pathogen. So this is something, for example, so you expect short delay, more connected, long delay, less connected, and you can build a model that encompasses how many susceptibles are in every city to get an estimate of connectivity of every city in a country. Brian Grenfell and Otto Bjornstad did this for the first time for England and Wales, and all the methods are explained there. And I ended up doing it to look at the distribution of how rubella was moving around Peru. So the red points are more connected than on average, and the blue points are less connected than the average. And the sort of red points are in the big cities, and the blue points are in the remote locations, so it sort of makes sense. And the reason I cared about this for rubella is that if you're in a really remote location where the infection is going extinct, again you have this problem where women can age into their childbearing years without ever seeing the infection. So we want to know where those places are, potentially to make vaccination available to women in that bracket, right? Because all this time that's happening between introductions is time when women could be getting older without ever getting infected, because there's no exposure to infection. Okay, and I quite like this because it's thinking about, you're seeing how connected the countries are, but from the perspective of the pathogen, and the degree to which this maps to like human road networks, etc., is quite fascinating. Okay, role of chance, seasonality, birth rates. One more piece before we take a little break, and that is individual heterogeneity. So we've been talking as if R0 was a single platonic number. It's 5 for rubella, it's 20 for measles. And of course, you're all biologists, or many of you are biologists. You're all sorts of things. But individual heterogeneity is just something that we generally see. And so this is a paper, a really sort of foundational paper in the field, Lloyd Smith et al. In 2005. I really recommend it if you're interested in this topic. It's kind of technical, but it's just beautiful. Where he looked at different infections and he plotted out the number of secondary cases per first case. So this should be R0, some measure of R0. And you can see that the mean tracks broadly what I've been telling you. Rubella is smaller than measles, smallpox is smaller than rubella, but there are these vast outliers. And so, for example, measles, it's somewhere around 20 secondary infections per primary infection. But there's this one guy who infected 204 people. And it turns out they knew exactly, so this is somebody who turned up, it was a sailor who turned up in Greenland where there was no measles at all. And he had measles and he went to a dance party and 204 people, like 2 weeks later, 204 people had measles. So that must have been really embarrassing. Anyway, so clearly individual heterogeneity is a thing. Ooh, Cowie.
I am having a little trouble trying to understand what this is. You have different populations and the number of secondary cases for those different populations. Okay, but the symbols represent the same population but why is there like 2 losanges in the same?
This is a great question, and thank you for asking it. So this is, I think this is they compiled information from a range of different studies. Apologies for moving so fast because I was excited to get to Greenland. And so in one study, the number of new infections per monkeypox infection was 1, the number of secondary infections. Whereas in another study, it was more like 5. This is on a log scale, so I'm not sure, etc. So these are all an array of different infections. I would have to look at the paper to figure out what the symbols mean, but this is my sense of how this is working. We should look at the paper together, how about?
Okay, because after you pointed to the losanges and dense part in Greenland, and then I thought all the others losanges are dense part in England. But then I noticed it was absurd and I couldn't figure out what it was.
Yeah, they're not all dance parties. But I would definitely have to look. I'll do that after class. Thank you, Gavin. Yeah. So one way that this paper suggests to represent this process is by allowing for a distribution of that R0 across individuals. And one thing that emerged from sort of glancing at this is there is a difference in how, what fraction of individuals is driving most of the cases, right? You all probably heard about the 20/80 rule. 20% of individuals drive 80% of onward transmission. Sometimes it's even fewer, right? Sometimes, however many people have it, only a very tiny number of them transmit it to the next individual. And this is what Jamie Lloyd-Smith's paper is trying to tackle. And the approach he uses is by looking at the distribution of an individual reproductive number, right? So instead of there being a platonic R0 for the population, I might have a value, you might have a value, we'd all have different values, and then someone would go to a dance party. And so this is, for example, a distribution where the mean is 1.5, but the degree of overdispersion, which is the term used to describe this, varies from being very tight to being massive. So this is a situation where most individuals are doing no onward transmission, and some individuals are doing huge amounts of onward transmission. And if you lay that onto, if we go back to looking at this probability of extinction for the different R0s, and you lay down these different degrees of overdispersion, what you find is that if something is super overdispersed, and so for example, we think that SARS-CoV-2 is pretty overdispersed, then since most individuals are resulting in no new infections, there's a very high chance that the infection will go extinct, right? Whereas if you're in a world where, everybody who gets infected on average infects 2 people, the thing has a much lower chance of going extinct. Does this make sense to people? Okay. But the problem is, although the probability of extinction might be much higher, the speed at which these things spread can also be much higher. So this is the time to get to the first generation with 100 cases for different dispersion parameters. And so these are the super overdispersed ones where a very few individuals are driving vast amounts of transmission. And in that case, it takes a really short, the first generation with 100 cases comes pretty quickly. Okay? So this is, explosive outbreaks are what happens in these super spreader areas. This is the example of the 2003 SARS-CoV outbreak, I think. This is I think it's the Singapore stuff. And of course, if you look at this as someone who's interested in controlling infectious diseases, you might be thinking, well, we just need to find these people, right? And tell them no dance parties. But more seriously, one never wishes to stigmatize people associated with infection, and one should think carefully about what that actually means. So I'm now going to ask you, how would you think about targeting superspreaders? Think about the infections you know, from the vector-borne to the human behavior. What do you think is driving superspreading, and how should we be thinking about using this in infectious disease control? How are you?
You mean in general?
Just give me anything. Give me a sense of what you think drives it, how you think.
Well, I tend to think that given certain activities which are more related to a certain disease, it is natural that due to sociability questions, issues, certain people have more centrality, and that happens in sociologically in many levels, from sexuality to the level of conversation, of how many conversations with different peoples you have. So it is natural for me that there should be people who with different levels of contact between amongst each other. So that's how I see it. You have to have a maximum of it.
Do you know that there's this wonderful result, which is that based on network science, which I'm sure many of you know, which is that your friends have more friends than you do. But even then, you know, it's very hard to find like, we don't have this type of surveillance on our populations, right? Where we actually can identify, and nor should we, I think, right? Like, quite strongly I feel we should not. And so there's a way in which all the social pieces are so important, but so intractable in an ethical society, right? But there's lots and lots of things that actually shape how much more transmissible some individuals than others. So I think you're absolutely right, Kawe. But one also has to consider that there are aspects of the pathogen, there are aspects of the environment. There's lots of different ways of becoming a super spreader. For SARS-CoV-2, there were people who sat in front of the air conditioner in the restaurant. They were identical to everybody else, but it was the environment that transformed that into being a super spreading event. So we can think about contact rate, as you listed, and the probability of transmission per contact might be behavior, but it might also be that for some reason I'm immunocompromised, my viral load is higher, I'm more likely to give it to people. It might be that, or you know, I'm more poor and I can't afford a level of hygiene that other people have. There's all sorts of ways in which different aspects of an individual can shape how much transmission happens. The infectious period can vary across individuals. Again, this could be about immunity, it could be about all sorts of things. There are different features of strain, so it might be that I have an incredibly transmissible strain, but you have a much milder strain. It could be that I live in a city or in a patch within a city where there's a lot more contact that happens. And it could be that I have access to care, so I'm much less likely to transmit it. So there's tons and tons of ways in which what shapes who is driving infection will play out, and we very rarely really understand what the full spectrum is. So we need to sort of think very carefully about how we manage these processes. There's a very classic example in the history of human infection called Typhoid Mary. Do you guys know about this? Yeah. Just let me. Well, I'll tell it. I can't make you tell it. So she was a cook. Correct me if I'm wrong. She was a cook in the late 1800s in New York, and she was a latent carrier of tuberculosis. And she didn't know. And she was a cook, and this was the only way she could make her living. So she killed a lot of people. But because, you know, so she went from a family, she was banned from working as a cook, but she didn't really understand what was going on. And they ended up sending her to live on an island by herself with no one to speak to. Because, you know, they're like, well, you're Typhoid Mary, you know, like even the term has its own stigma. So I think there's, it's certainly a huge factor in understanding the spread of infectious diseases, but it's one with a vast amount of nuance around it. Okay, so what I'm going to do now, it's a person, yeah.
But that's an expression, I didn't know.
Is it an expression or? So I think in certain Anglophone-ish sections, like if I referred to, I think maybe there was a phase where people would refer to someone as a Typhoid Mary, like but I think that's gone out. But the term still, like my mother used it, for example, not about me, but it's something certainly that I heard growing up. Okay, I'm going to give you a break, and then we're going to come back, and then I'm going to talk a little bit more about some of the public health work I've centered around this stuff based on a request from David. And from that inspiration, if you want stuff, request it, right? We're trying to make this something that people find interesting, so certainly come to us and ask for more. So if you want to come back at 12:35. Oh, you got it? All right. Thank you for returning. Okay. So I told you how I entered into thinking about public health on rubella. But if you're thinking about rubella, it is almost inevitable that you think about measles. A directly transmitted, completely immunizing infection, so the usual schematic, a safe, inexpensive, and completely immunizing vaccine, as we've been discussing. But also, this is an infection for which, in the worst case, the case fatality rate can be as high as 20%. It really is, this vaccine is referred to often as a best buy in public health because it is so cheap and it is so effective and it protects children for life. But of course, the trick is getting vaccines into children. And we have a sort of pretty poor understanding of what the distribution of vaccine is and what the limits are in many of the more resource-poor settings in the world. So one of the first things I did in this area was look at travel time against vaccination coverage in places in Sub-Saharan Africa, which is some of the places where vaccine coverage is lowest. And for this, I used data from the demographic health surveys. You may have not encountered them. They are amongst, on a PDF listed that I've given to you. And it's a kind of incredible source because they do these huge cross-sectional surveys of the population where they ask a bunch of questions of mothers and they record it all and it's freely available so you can use it to probe all sorts of questions. They're still probably underused. So what I did was, because they had the GPS coordinates of all these children, I put this together with vaccination coverage reports to look at how much travel time to the nearest city of, I think it was 50,000 people. Yes, 50,000 people was related to vaccination coverage. And this is what the patterns look like. And so this is in 1-year-olds in blue and in 5-year-olds in pink, in all these different countries. So Nigeria, Ethiopia, Sierra Leone, Guinea, etc. And the reason that 5-year-olds have more coverage than 1-year-olds, I hope should be obvious. It's, you're reaching more and more as you go through time, and so 5-year-olds have had more opportunities to be vaccinated. And amongst the things you can notice is that it's pretty variable, but there are places where it's very clear that the further away that children have to travel to get to a big city, the less vaccination coverage they have. Ben and I do a lot of work in Madagascar, as you probably has become clear. And so we looked in particular at vaccination coverage in Madagascar. This is what that looks like by 1 year and by 5 years. And if you narrow in on what the range is between the most remote locations, so in green here, to the least remote locations, you can see that there's vast inequity across the country. Yes?
Just a little question. I don't understand what the graph is saying about the time. So,
This one?
yes, it's like.
How long it would take you to travel to the nearest city of 50,000 people.
But why always the graph ends in hours? It's like.
Oh, so that was the furthest we went out. So beyond that was our threshold. A very small fraction of the population, even in these places, lived much beyond that.
Oh, okay.
And if they lived much beyond that, I think they probably wouldn't be in the data very much, unfortunately. So this is what we did. And we used a pretty simple, just a sort of spline regression to get at what these patterns were. We weren't being mechanistic or terribly sort of careful. This is very phenomenological modeling. Okay. And so this is just ranking all these different countries in a bunch of different surveys in terms of their maximum coverage achieved across all the data we had in the most remote locations to the closest locations. And you can see that some places have both high coverage and are very equitable. It doesn't matter how far away you live from a big city, you're getting vaccinated the same as your cousin who's in the city. But there's some places where it's a very big difference, and that tends to go alongside with low coverage. So places that have lower coverage, also more inequitable. Not shocking, but of course sad. Madagascar, if we narrow in on Madagascar, there's this big difference between the rural kids and the urban kids. And we also did something where we said, okay, what if you were to imagine that you could build roads and make this travel penalty go away? How much would you improve things? This is a kind of complete fantasy, but it's the kind of fantasy you can do with a model, right? You can ask, what would happen if I just made that better? And Madagascar was one of the places that had the biggest benefit, the biggest increase in vaccination coverage in those terms. Now this all matters because we were looking at Madagascar's cases, so this is vaccination coverage reported to UNICEF, and this is measles cases, which drops sharply around 2006 and then stays at really very low levels, so less than 10 cases per year for like over a decade, right? Which suggests that they're doing something awesome, that they're really controlling measles, which would be great news. But it's also like surprising news if you've seen those results on the inequity on the coverage. And what we were worried about was, you could have this pattern in two cases, right? One would be where your vaccination coverage is huge, it's solid, nobody's getting infected because everybody has been immunized the right way, which is by vaccination, instead of the wrong way, which is by infection. Or it could be that you've driven measles extinct. You've done really well and you've driven measles extinct in many parts of the country, but your vaccination coverage is not that good. So over this time period where there's little measles circulating, there's a buildup of susceptible children. So every year, children are born who are not getting vaccinated, and there's going to be more and more of them, right? So you can imagine this is referred to often as a honeymoon period. Susceptibles are going to fluctuate slightly off time with the numbers of cases. You drive the cases extinct, the susceptibles might stop, will stop being depleted by infection, and so they could start growing, right? And they might grow up above that threshold for R0 times S to be bigger than 1. So they could be a new outbreak. That's the worry. And you can see that if you have a really high birth rate and low vaccination coverage, since children are being born every year, you're going to end up growing up above that threshold really quickly. Or if you're in a situation where you have a low birth rate and high vaccination coverage, it might take longer. And what's happening across this span, because nowhere is completely isolated, is that people are turning up with measles, right? People are flying into Tana, or maybe there's little pockets of transmission that are still happening. And so you might get unsuccessful introductions during all the time when you're below that threshold of susceptibles, but there'll come a time when you're above the threshold and you'll get outbreaks again. And so we wanted to know, were we in this phase where Madagascar was at risk of an outbreak, or were we not? And it obviously matters. How long, so this was referred to as a honeymoon period. The woman who came up with the term, very eminent, Angela McLean, came up with it on her honeymoon. She was in Guinea with her husband at the time, and she was talking to the measles program officers, and they were so upset. They said, we have this huge outbreak, and we don't understand. Like, nothing has changed. We've been doing the same thing for the last 10 years, but suddenly there's this big number of cases. And she realized that what could have been happening was that although they were doing the same thing for the last 10 years, it wasn't enough. So secretly, under the surface, the iceberg was growing, the number of susceptible children was growing. So when the outbreak happened, it was really bad. So this is our SIR model. This is an example of a health center in Madagascar. And the problem is, right, what we want to know is this. What we care about is where we are in those terms. What's reported, what we see, is only ever cases. What happens in Madagascar is that if a child has fever or rash, if the health system is mildly functional, which it often isn't, that child goes to a center, the doctor takes a blood sample, it's sent into the capital, and it's tested for measles, IgM. So IgM is a short-term marker of infection. You might say, well, maybe we're only seeing 10 cases over the last decade because the reporting system is a disaster. It turns out that's probably not the case, and that's because the same reporting system reports rubella, which, as I told you, is much milder. So if you're catching any rubella, and the reporting system is catching rubella, you're probably catching measles, right? So this is the data from the last sort of decades preceding that. So we didn't believe that the reporting system was completely broken. We thought that it probably was realistic that the number of measles cases was very low. And so we were worried. And what we realized we could do was, because the reference laboratory had kept all these samples, all the fever rash samples that had tested positive for rubella, all the ones that had tested positive for measles, and all the ones that had tested positive for neither. They had them all in their freezers. And so we realized we could go in and test them for IgG. And so this is a marker that tells you who is susceptible and who isn't. All of you in this room will have positive IgG markers because you were all vaccinated against measles. Except for me, my mother was a refuser, I had measles. So I'm positive, but for the wrong reasons. So that gives us, suddenly we can figure out the size of this risk pool, right? By doing this testing. And this is work that was led by a wonderful graduate student of mine, Amy Winter, and this is what she found. So this is the proportion
of seropositive, so who are immune, over age. And obviously what we want is this to be close to 100%, and what she found was something much more wobbly. And it was wobbly in ways that were super surprising, because this is when the children who are eligible for the campaign that happened in 2004, you'd think that at least these children would all have been vaccinated and they'd be up at 1, but no. There was another campaign in 2007. Again, you're seeing, if anything, like during campaigns, it seems like seropositivity goes down. So that's not great. But what we really cared about is what is the risk of an outbreak? Given this profile of susceptibility, is Madagascar at risk of an outbreak? And so what you can do to evaluate this is, of course, build a model. And you can do vast sensitivity analysis. You can imagine all possible futures. You can test different patterns of contact over age, because these matter, right, in terms of who's talking to who and how the disease is spreading. You can test different interventions, different vaccination campaigns, and you can see what happens to RE. So this is what we did. So SIAs are vaccination campaigns, and we looked at what would happen if you did no vaccination campaign, if you vaccinated everybody from 9 months to 5 years, and so on. And we did different age profiles. We really tried to kick it every way we could. And what we estimated in all these instances is what was the R effective. So that gives you a sense of whether there's going to be an outbreak or not. And the related measure, which is the proportion susceptible, right? Because they are reverse mirror images of each other. And this is what we found. So everywhere, this is the threshold for there being an outbreak. Really, even if you did the most extreme supplementary immunization, like the most wide range age campaigns, we were at risk of an outbreak. And so we published this in 2018. We talked a lot to the World Health Organization. We talked to everybody. And very tragically, that outbreak happened that year. And thousands of children died. It was really, really sad. And it was really hard. It was really hard because the information was there, but they couldn't get the funding to come in on time. There just wasn't the responsiveness from the global community to grapple with this problem that we knew was going to happen, that we had predicted using this measure. The classic epidemiologists in the room might be thinking, this is a terrible sample, right? Like fever rash surveillance is so erratic, it's not representative of the population, it's all over the place. But I think the philosophy that we brought to this was like, it's the information we have. And the thing that models let us do is test everything, is try and kick our sensitivity analysis to make sure that we believe our prediction. And we believed our prediction, and unfortunately, we were borne out by what happened. This is that picture I showed you, and then the number of cases leapt up to the levels that had been before. It was clearly a honeymoon period outbreak. And this is work that was led by Ansu Harindrasana in BMJ Global Health, where she looked at this is how that outbreak happened across different regions in Madagascar. And the vertical lines show you when the vaccines came in different regions in Madagascar. And I think you can see just by looking at this picture that the vaccines came too late, right? They're happening, if anything, after the peaks of infection. It just couldn't mobilize the money, couldn't mobilize the vaccines. But we can still do the detective work, and Ansu led a lot of detective work on trying to figure out exactly how this had happened. And one of the things you can do using the demographic health survey data is pull together estimates of vaccination coverage and look at what that does to the average age. And the idea here was that, in fact, doing well at vaccination had, in a way, put you in a bad place, because it meant that your children were not being immunized the wrong way, right? You'd had a buildup of susceptibles. And so this is what we saw. If in places that had done really well in 2009, so that was like a decade ago, they'd kept measles down to such low levels, but they kept missing, not vaccinating everybody. And so they had a buildup of these older children who were still vulnerable to infection. However, there were some places that weren't so good at vaccination. And in those places, measles was probably still circulating, although our surveillance system was not picking it up, so those children were still probably immune. You could map out RE, R effective, in the same way, and again, we're finding that R effective, which maps to that proportion susceptible, which tells you this vast age bin of kids that were still susceptible, has that same pattern with vaccination coverage. So this, the work happened before to say the problem was happening. There was detective work led by Ansu afterwards to try and grapple with what the determinants would be. And then Ansu also spun to think about what this meant. What are lessons that could have been learned from this measles outbreak in Madagascar for the world more globally? And this is not a unique problem, right? The time that we wrote this paper, there was tons and tons of these huge post-honeymoon outbreaks for measles in many parts of the world. This is data from the World Health Organization that shows these sorts of processes, and so we sort of probed and tried to think generally about this using this basic framework. And I'm sure it's obvious to you from this framework, but you can think about that risk of the honeymoon, that delay until you get that honeymoon outbreak is going to be driven by how fast your susceptibles are growing, because if they're growing really fast, it's going to happen really soon. But also that rate of arrival of infected individuals per year, right? If nobody turns up, you've got a longer time that will give you a chance to try and get to grips, vaccinate your population. It's possible that Madagascar was somewhere down here. We don't know exactly. It's very hard to actually carefully document human patterns of travel. Like, I do a lot of work with mobile phone call data records, do a lot of work with airline flows. It's actually really hard to pin down disease-relevant travel of people. And so although I think we should keep working on understanding human-related travel, the thing that's actually tractable to us is that thing that Amy Winter did in that first part of this talk, which is measuring susceptible growth. And this is something that myself and colleagues have called for a lot, which is that we should have a global immunological observatory, right? We have weather forecasting changed dramatically the moment people put out buoys to measure the surface of temperature of the sea. In a funny way, we actually have the best sensor possible for infectious diseases, which is ourselves, and we're not measuring it. And yet we have blood samples all over the world. We have them in blood banks, we have them in like this fever rash surveillance, we have a lot of HIV testing per year, which we could be using, I could go out and test all of you and I could figure out what flu strains you've been exposed to, whether you're immune to measles, is there a risk of an outbreak of rubella? All of that information is there, but we're really not using it. And yet it seems like it's a vast missed opportunity, both because there's huge technological advances where you can, for example, take linear epitopes, so you can take every single virus that's been known to infect people, and that's only like 220 or something, that is a small number, and put them on a chip displayed by phages, show them to your blood and find out what your blood recognizes. Everything. Sorry. Which would give us this extraordinary window onto this landscape of immunity, which doesn't just, the thing it has above cases are very short-lived, right? You manifest measles only for a couple of weeks, but your immunity to measles you have for life. So it gives us a window back into the past, but it also tells us what the future might hold. So this is one of the things that we have been framing and trying to come up with test cases that illustrate the power of it in many parts of our research. And just the last slide here gives you the 3 papers led by these 3 wonderful people. And we also got to do this work with the head of WHO in Madagascar, Julio Rakutunarin, who was the Minister of Public Health, Minister of Health at the time, and then Yvonne Massemba, who's a great person at WHO. I can talk more. There are other examples. I mean, the hardest thing in the world is to come up with an intervention or an insight that is cheap and easy to implement. We very satisfyingly did this for a seasonal measles vaccination in Madagascar, and this was because we discovered, by looking at the data, that vaccination was actually only really occurring twice a year. Ideally, children would be vaccinated at age 9 months every time, whenever they reach 9 months. But because of supply chain issues, because of logistical challenges, what ended up happening is they would vaccinate a bunch of children just twice a year. And they would vaccinate children between like 9 and 12 months, just twice a year. And that meant you could be born at a time when you would never get vaccination. It's that simple. And you wouldn't see it unless you really looked at the data, but we really looked at the data. And we went out, so Kately went out and digitized a bunch of vaccination cards to get at this. And what you can say there, which is so satisfying, is just say, relax that upper age range. That's all you have to do to fix this problem. And it's incredibly cheap. So that is the most satisfying piece of public health recommendation I've ever done. But there are many other threads around it. Anyway, I think that's it for today. Any questions, any suggestions for tomorrow, let us know. We'll stick around for 5 minutes, and then I guess we go for lunch. Oh.